going to discuss right now in this, that is the particulate nature of the electromagnetic waves. Actually, this is the part of quantum physics, right? So honestly speaking, if I consider this all for you, you people will just get one part of the, yani 50% of unit 2 will be sorry, 25% of the unit 2 will be clear from this one. Okay, so particulate nature, actually there was a Planck's theory which was established by Max Planck, and in that theory it was, is my voice clear and everything?
Yeah, clear.
Okay, it was said that all the electromagnetic waves, they travel in the form of photons, and basically these photons carrying the waves, sorry, inside, and they are basically the packets of energy. And if these are the packets of the energy, the energy of each packet is directly proportional to the frequency of the photon inside it. That is why the Planck suggested this equation or relation that E is directly proportional to frequency, and then we came to now that E is equal to HF. Now this H is Planck's constant, and its value is 6.63 into 10 raised power minus 34 joules second. This is the value for the Planck's constant, and once we divide that, yes, one more here I have just put, I have replaced this, that V is equals to F lambda is an equation which is used as a main wave equation, and from here V, frequency is V by lambda, and this V is basically the speed of electromagnetic waves. That is why I just considered it C by lambda. So is there any confusion in this equation? These are the three equations you have to recall, and these are the three equations from where you will be asked about the question. So is there any confusion, or you want to ask me something related to this?
This formula will be given.
Yeah, this
Or,
formula will be, yeah, this C by lambda is, I think you have to recall this all. HC
okay.
by lambda, right? Planck's constant value will be given to you, okay? The value of Planck's constant will be given to you, but the
Yeah.
formula HC by lambda is to recall, okay? Okay, should I move on? Now, this is basically very interesting point, that when we talk about uh, wave particle duality, there was a situation, and that situation was basically discussed, situation where the electrons were having a sort of, you know electrons were passed through the diffraction grating, or electrons were passed through the Young's double slit experiment, and those electrons responded, that they responded just like the waves. Why? Because they made some circles, or they result some circles. In those circles, these are those areas where most of the electrons were bombarded, or most of the electrons were just reached. So we call it the maximum level of intensity or maximum intensity points. And these were the areas where no electrons was reached. So this is basically the minimum intensity level. So these maximum and minimum intensity levels were the same as that of your, uh, you know, as that of your diffraction and interference. So if a particle is behaving like this, or if a particle is performing the interference or diffraction, it means that this particle has a wave nature. So that is why your de Broglie wave equation came into being, which is your, I think so. This is the. Did you people specification of your syllabus ever? Syllabus, course syllabus, कभी go through गया?
I did once.
Yes. So this de Broglie wave equation is the part of your syllabus. Here I have just started entire discussion right from here. Okay.
Mhm.
Now this experiment, which was basically the wave particle duality experiment, the de Broglie extracted two concepts. One of them was that if there is a particle, then that must have an energy in the form of E is equals to mc square. And if this particle is filled with the waves, yani the photons, then this particle must have the energy, or these waves must have the energy E is equal to hc by lambda. So actually, if I simply say that this is the quantum or quanta or one photon which has all these
No.
Mm-hmm.
waves inside, then what happens? Yeah. Is there any problem? Sorry, just okay. Just say again. Who is there?
Sorry. Nothing.
Yes, Yusuf. You want to say something?
No, no, sorry.
Okay. So, is there anyone who is asking me any question? कोई question आप लोगों का?
नहीं सर वो यूसुफ का माइक था आवाज आई थी on the background he was saying yes.
Okay, 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 okay. That's fine. Sorry, I thought that there is any question with me. So I was saying that these photons are basically having energy in the form of this wave equation E is equal to hc by lambda. That is why he merged both these equations at E is equal to mc square and E is equal to hc by lambda together. And by this, he got an equation that is c is basically speed, so c will be cut by this. So you got that m into c is equal to h by lambda, and m into c is basically momentum of that electromagnetic wave, and which is equal to h by lambda. So this lambda is equal to h by p is the de Broglie equation, which is also an important part of that. And here we can consider that yes, if we have the de Broglie wavelength, the de Broglie wavelength is defined as yes. Here you can define the de Broglie wavelength in this here in the line that the wave associated with a moving particle is called de Broglie wavelength. It's a very simple concept. Can extend this just for a while. For example, if I say that an electron is, I want to calculate the wavelength associated with an electron. So lambda is equals to h divided by momentum of that. So let's add a page here. I don't know why the page is not being added here. Space. No. Okay. In these notes, there was a problem that I was not able to add the space. So I would calculate right here that if I say that I want to calculate the wavelength associated with with an electron, so that means that I must have that lambda is equal to h by p, and p is m into c. So h divided by m into c. So ordinary speed of the electron is 1/10 of a light. So 6.63 into 10 is power minus 34 divided by this mass of the electron is 9.02. It is also given to you there into 10 raised power minus 31 into it is 6 into 10 raised power 6. So almost if you calculate this, you will say that it is almost 12 nanometer. Almost, right? Sorry, 1200 nanometer. When you will calculate this, because I have calculated it times and again, that is why I believe that it is almost 1200 nanometer. So this 1200 nanometer is out of our visibility range. Do you remember? You cannot basically see an electron because our limit is 400 nanometer till 700 nanometer. You got this point? So that is why the electron has to be very slow, almost 2000 meter per second pe aana chahiye. Then you will be able to see the electron associated wave. So that is the problem. That one more thing, that why in ordinary level we don't observe the diffraction, because for these big particles, macro particles, we do not have that lattice space which can cause the diffraction there. So there are several facts and factors about this all. So I believe that it would be when we will discuss them in detail in the past paper practice, it would be clear to you. Yani, there would be more details in the question. I will try to send you some worksheets regarding this also, so that we can mm, uh, handle the questions. Then we have the photoelectric effect. The photoelectric effect is basically the second part of your quantum mechanics. In the photoelectric effect, basically, uh, once we consider the concept of this photon is sent to you. This photon is sent on a metal to extract the electrons from the metal. So that is why this emission of the photo electrons, or this emission of electrons from the surface of the metal, is called your photo emission. Right? The photo emission has several concepts. Yani, there are several types of detailed notes I have on this. These are the short version of the notes. So actually, you know what happens? This is the metal, and once the photons are incident on this metal, the electrons will be stuck out, and remaining metal will be positively charged. And when I will bring any charge detector closer to it, then what will happen? That charge detector will consider that, oh yes, there is a charge over there. So Einstein in 1905 or 1907, I think, I'm not quite sure about the dates, but he worked this setup, and this setup was basically named as your photocell, or usually now we call that photos. I mean, uh, solar panel is based on this all, right? So that means that what did he do? He just uh, managed one thing, that a metal was placed in front of the light source. Light, I mean, I can say that there is a lamp, and that lamp is able to generate the light of different wavelengths and different intensities, and that light is incident on the metal. So when that is incident on the metal, then the electrons are released out. These electrons, these blues are the electrons liberated out, and those electrons reach to this collector anode, and with the help of this uh, variable resistor, what did we do? We just control the current, amount of current. This is the variable voltage source as well, and this is a milliammeter. Actually, this is the masterpiece here. This milliammeter is to show that whether some electron has been released or not. Okay, so this is its basic structure. Now the simple conditions are there, that how does it work. Yani this is basically the working conditions, right? The working conditions are, there must be a frequency, right? There must be a frequency of the photons, which is called threshold frequency. What do we call it? Threshold frequency. So threshold frequency is the frequency at which the emission just starts up. You got this point? Threshold frequency क्या होता है? The minimum amount of frequency at which the emission just started. Okay, that is why we call the, okay, yeah, thresholds are basically some grade levels. Threshold levels are there, grade boundaries. Yeah, these words are very common in in your students' life as well. So this is that every energy or every frequency is not sufficient to extract the, or to release the electrons, but these electrons are released at a specific frequency, and that specific frequency is basically called threshold frequency. Then work function energy is another term, you have to recall this please, and you have to manage this also. Work function is represented by phi, and its unit is joule. This is the energy corresponding to that threshold frequency. Yani, as I told you, that the waves have yani the photons have threshold frequency. That threshold frequency, because I told you that the formula E is equals to HF, is the foundation formula of your quantum mechanics or quantum physics. So by that formula, if I need the energy which is the basic energy, then that basic energy will correspond a specific frequency, the minimum frequency. Yani this minimum frequency is corresponding to this minimum energy, and this minimum energy is corresponding with this minimum frequency. So that is why it is called your threshold frequency, or this is also called your work energy, sorry, work function energy. Okay, you can calculate the work function energy of different metals, for example, on different metals. Actually, in this all situation, there is one problem that I wanted to address with you, that your calculations are in electron volts mostly. Electron volt. Are you people aware of the electron volt? Electron volt is the unit of energy. And for example, if I say that for any metal, the energy is released when when the frequency is starting by the red wave, right? So that can be also written in the form of hc by lambda naught, hc by lambda naught. So this hc by lambda naught, I'm using this over here to calculate the energy of work function energy of that metal, that h c upon lambda naught. H is 6.63 into 10 raised power minus 34 into 3.0 into 10 raised power 8 upon lambda naught for red color, that is 700 into 10 raised power minus 9. So can anybody please help me out to calculate this rapidly? Speed up, please. Yes, is there anyone?
2.8 times 10 power minus 19.
Yes, this is basically joules. So this is very small amount of energy. That is why what do we do? We divide this number by a value which is 2.8 into 10 raised power minus 19 divided by 1.6 into 10 raised power minus 19. This is to convert this all into electrons volt, EV. Remember this thing. Is this clear to everyone?
Hmm.
Sir, could you please repeat?
Yes, I'm saying that the energy basically here, that is your energy in the form of joules, right? That energy is in the form of joules. Let me share one more file with you. I hope that that was uh, here. Just give me a second. I want to write something for you, basically, but in this file, unfortunately, I don't know why there is not space. Just give me a second. I will add new notes on this side and I will put some calculations for you. Okay, the calculations here are actually based on this all, uh, you know, the work function and all that stuff. For example, I will just do calculations here. Okay, on this slide. Is it visible to everyone?
Yes.
Yes, sir, it is.
Okay, both of these screens. I told you that basically every metal has its different work function. Okay, right? Work function energy. This is your work function energy. Let me write all the stuff for you. Work function energy, and that work function energy is basically equals to HF naught. And as I told you, that this HF naught can also be written as HC by lambda. I was saying that if the threshold frequency is the red color wave, okay, or that is for a metal is responding at red color, whose wavelength is equals to 700 nanometer, then I will simply plug these values in. That work function is 6.63 into 10 raised power minus 34 into 3.0 into 10 raised power 8 positive 8 divided by this wavelength 700 into 10 raised power minus 9. Um, Yusuf told me it was 2.8 into 10 raised power minus 19 because this is your energy. So its unit is joule. So I have written joule here. Is this clear to everyone? Is it
Hmm.
clear?
Yeah.
Okay. So right after this, there is one problem, one more problem. This is very small amount of energy. So to convert joule to electron volt, what do we do? Divide the value of joule with Ilaf. You know, 1 joule is equal
Yes,
to how many electron volts?
1.6 into 10 raised to minus 19.
Yes, 1 joule is equals to, sorry. 1 electron volt, 1 electron volt is equals to 1.6 into 10 raised power minus 19 joules. Okay, this is very important, and you have to remember this. One electron volt is equal to this. Yani, if I say that I want to calculate 1 joule is equal to what? 1 divided by 1.6 into 10 raised power minus 19 electron volt. So how many joules do I have? I have, or I had 2.8 into 10 raised power minus 19 joules. That is equals to 2.8 into 10 raised power minus 19 divided by 1.6 into 10 raised power minus 19. Now this is in electron volt. Is this clear, Umar, Ilaf, Yusuf, and who is
Yes,
there?
sir.
No,
Okay.
sir.
फातिमा ने ज्वाइन किया हुआ है?
No,
उमैर
sir.
और
No.
फातिमा?
No, sir. Fatma is not over here. Umar is
Okay. So this is basically what ये मुझे values बताइए. What is the value you are getting here?
1.75.
1.75 electron volt. Yani this is a significant value which I can basically consider that yes, there is some energy. So this is basically the minimum required energy to just release an electron from the surface of a metal. Right? Is this clear to everyone?
Yeah.
Minimum amount of energy required to release an electron from the surface of metal. Okay? Is it clear to everyone? Now,
Yes, sir.
if you are going to give more energy, then that electron will have the kinetic energy also. Right? So I am just going to write that kinetic energy of emitted electron. Right? Definitely that electron which is released from the metal surface, it will move. Right? That was the metal, and the electron was released from the surface of the metal this way, and it is moving. So it will have some kinetic energy. If it just dropped here, it does not have kinetic energy. But if it is to be, or if it is reaching to this, this was basically the photovoltaic cell. So I just draw half of its part which was required for me, right? I just need that part. Okay, is it clear? So basically, I just did very simple assumption. I made it very simple. This electron has to jump from this metal to this collector. Then you can register the current in this emitter. Na? Is it possible? Is it easy? Do you understand this concept?
Yeah.
For this purpose, this electron must have kinetic energy. From where this kinetic energy comes, the energy of the incident photon, E of the photon, is divided into two parts. That is equals to E of the work function, energy of work function, or you can say work function energy, plus kinetic energy of electron. That's very simple understanding that the total energy, that is equal to HF, that is divided into two parts. One is HF naught, the other one is kinetic energy of the electron. Kinetic energy of the electron. So if I want to find out the kinetic energy of the electron, that is HF minus HF naught. Is it clear? So you can take H common. So this is basically the difference of threshold frequency and the incident photon energy. That means that if you have this kinetic energy here, this is the value of kinetic energy. Is this clear?
yes, sir.
Okay, I can simply write this equation in this way, that Ke is equals to HF Sorry, just a second. HF is equals to work function plus kinetic energy. Are you agreed with this equation? देखो, whatever will be the energy of the incident photon, it will be divided into two parts. One that is equals to its work function and for work function energy, and second one its kinetic energy. And kinetic energy is basically that also that can also be written as HF is equal to work function plus 1/2 mv square. Are you getting this point?
Mm-hmm.
Yes, sir.
You got this?
Yes.
Yes, sir.
Okay. So you people will have plenty of calculations for this all, right? That how to calculate the maximum kinetic energy or how to determine the Ke maximum. Actually, for Ke maximum, what do? We just rearrange this setup in this way that the electron and electrode and this all is in front of each other. The battery terminals are now reversed. Battery terminals are now reversed. So what will happen? This is a critical concept. I believe that you people will get it. Dekho, if a single electron is liberated from this metal, this electron is, I'm just going to zoom it in. This is the negative electron, right? This electron was having attraction before that. It was having an attraction. Sorry, I just drew it incorrect. Yeah, now it is correct. Because now you have applied a negative terminal on that side. So this is no more anode. This is a cathode actually. You believe this thing or not? This is a cathode. So cathode has a repulsion for this upcoming electron or incoming electron. So only that electron will be able to reach this anode, or sorry, reach this collector, which is having very strong kinetic energy. You got this point? Otherwise, all will be repelled, and the current is going to decrease and decrease and decrease. So current will be decreased. So finally, when the current is almost zero, then we say that the electron which is reaching here, that is the king electron, yani the most energetic electron. Why? Because you are going to make this voltages more and more and more reversed. Okay.
Yeah.
So once you are going to make it more and more and more reverse, actually only those electrons will cross this barrier. It's a squid game actually, simple. So those electrons will reach here, which are having that much high kinetic energy. So the energy of that electron is called maximum kinetic energy, and that energy depends upon the voltage is over here. Voltage is over here, right? It is called stopping voltages. What do we call it? We call it stopping voltage. The electrons are stopped to move. So that is why maximum kinetic energy is equals to E into V stopping, Vs. So if you are going to calculate the maximum speed of any electron, you can just calculate in this way, and you need some voltages across the anode or across this collector, and then you can find it all. Okay, is this clear to everyone?
Yeah.
Okay, then this was basically having another concept of, yeah, this all is actually mentioned here also, but because I was going to discuss KR, yes, one more thing from the same topic. I had just considered one equation that, yes, when I am saying that the entire energy is converted into this work function, yeah, this entire energy is formed as kinetic energy. So you can make this work function zero here in this equation. Let me write this equation again. So HF is equals to 1/2 mv square plus work function. So when work function goes to 0, this is gone. So then your HF will be entirely converted into mv square. So this is also another method to calculate the maximum kinetic energy of the metal, right? Maximum. But this is for surface electrons. Remember this thing. This is very interesting point. This is applicable for surface electrons only. Okay, is it clear? Now the next discussion about this all. This is very important graph for you all. That graph means the, this is the graph of frequency and energy. Okay, energy frequency graph. And this graph tells you about that from 0 to this level, there is nothing happening. So 0 to this red level, there is nothing happening. But that point where this red color red color wave is yani red line is showing, this is the threshold frequency of metal 1, and this one is the threshold frequency of metal 2. So let's say I'm calling it metal A and I'm calling it metal B. Metal A has smaller threshold frequency. That is why, did you notice its work function is smaller also, and work function is basically equal to y intercept. Y intercept. Yani, it's just nothing. Just go ahead. I had considered this all, that E is equals to uh, H F. Yani, this is the kinetic energy minus work function, isn't it? Anna? So just if I make it Y is equals to mx plus c, then did you notice that from here, this h is the gradient of this graph, this frequency is along x-axis, and this y-intercept is negative here. So negative y-intercept means c is negative. Negative c is where below the x-axis. Is it clear to all of you? So those metals which have more threshold frequency, they have basically more values. Now, just finally talking about this, because this topic has beauty lying in this portion, that why, what was the expectations of Einstein while he was performing this experiment, or any of the scientists? Because in that time scientists were swapping their experiments, that it was expected that once we are going to incident the light, immediately the emission was to be started, but it was not happening. Emission just started at very high frequency, and yani, the metals need more energy. So that was one of the expectations. Second expectation was that, okay, if it happened, that then when you are going to increase the frequency, there should be more electrons emitted. Emission of electrons should be more. This was the second expectation. Are you getting my point? By chemistry, if I'm going to apply more energy to the metal, higher frequency mean more energy, then more ionization will take place, and the electrons would be liberated more quickly, isn't it? Or more electrons will be there. So this was basically that more electrons should be emitted out at the same brightness. If the brightness is kept constant by increasing the frequency, do you know what is frequency? I wanted to make you clear everything, but sometimes the we have the race with the game, race with the time. That is why the frequency means color. If you have used different colors of the waves, colors of the light, then at the same brightness means intensity, you have kept them all at the equal distance. You must have, this was the expectation, that at higher frequencies more electrons would be emitted out, but at lower frequencies less, but it did not happen. What were the observations? The observations were very contradictory. No, it increased kinetic energy. The emission of the emission rate increased when for the same frequency, but brightness of the light increased. Check this one out. Yani, let me explain to you. This is basically the answer of this first. First expectation was the light is a wave, so at higher frequency, more electrons should be liberated. No, the more electrons were not liberated when you were increasing the frequency. What was happening? The kinetic energy was increasing only, right? And secondly, rate of emission, which was the emission, which is called the electron emission, or which is called the current basically, that was not increased. So that was increased when you have increased the brightness of the light, right? When you increase the brightness of the light, but you kept the Ke unchanged. You kept the Ke unchanged. This shows that the photoelectron effect does not take place due to wave nature of the light. It's very simple. I will give you some detailed notes as well, right? But there was a particulate nature, the explanation of particulate nature. What was the evidence in the particulate nature? Actually, in particulate nature, the scientists were in the opinion brightness means more number of photons incident. Did you ever heard today the rain is of very high intensity? The intensity of the rain is very high. Did you ever heard this? It means more raindrops are there. Is it or not? The raindrops are more. So when there will be more raindrops, there will be more intensity. So increasing the incident photons, the amount of or the number of the electrons will be increased. Yani every photon will liberate or every photon will release one electron, right? Single electron. So for one electron emission, one photon is required. That is the evidence that yes, in quantum mechanics, we consider that a single photon, single electron, right? One photon is required for one electron. It is not mandatory that if there is one photon of very high energy, it will just avalanche the different electrons or more than one electron. So this was one of the drawback or one of the evidence of that. So here I have considered the stopping voltages and the concept of stopping voltages, that V maximum is equal to E into V stopping. From here you can calculate that what would be the maximum energy and maximum speed of the electron which could be required there. Here I have just added all these things what were required by you, and this is basically the last discussion of my topic, today's topic, the transition levels. They are also based on the quantum mechanics. That the transition levels are basically those levels which are considered to be that okay. They go. It's very interesting thing. The Neil Bohr in 1913 he has developed an idea that if you have uh, if an electron is in this orbit, it will revolve in this orbit. It will neither emit the energy, neither it will release the energy. So that is why this was named as its energy level. What is that? That is called its energy level. Once the electron is to be moved to the higher energy level, right? It is the higher energy level. This is the lower energy level, lower energy level. Then that electron will absorb the energy. And when it is coming down back to the lower energy level, it will release the energy. And this is what I have shown you here, that when the electron is in cell number E1, energy level E1, it absorbs the energy. And it when it absorbs the energy, it gives a rise to the transition from lower energy level to the higher energy level, and we call it an absorption spectral line. Why? Because an electron, yes, there is a theory behind it. The bunch of photon was coming from this side, right? And that bunch of photon, of one of the photon was absorbed by the metal, and that photon is used to increase the level of this E1 electron to E2, right? And for example, if there is another photon absorbed, that will use to increase the level of this to E2, E3, and so forth. So when the photons are absorbed, they give a rise to the transition from lower energy level to the higher energy level. But once the electrons jump down from higher energy level to lower energy level, what do? They give the photons at the output. So this is basically, that is why it is called emission spectrum. Spectrum means they give a range of photons, several photons will be there. That is why it is called a spectrum. So the all calculations which are required here, they are based on this formula. that the energy levels difference is E2 minus E1, and that can be calculated, or that can be used to calculate the wavelength of the emitted photon. For example, an electron has been uh, transited between the energy level of minus 3.5 electron volt uh, and minus 1.5 electron volt. Then this is basically, you will calculate that 1.5 minus 3.5 into 1.6 into 10 raised power minus 19. This all is basically used into joules, right? And then you will multiply that by hc by lambda. From here you can calculate wave. Is it clear? So I tried my best to give you the maximum comprehensive details in the shortest time interval what I have. But in that case, definitely I have uh, shortened some details, or I have just paced up my work. So to support that, I'm gonna share these notes to you. So if you people have any of the issue, or if you want to ask anything from after going all through all these notes, I'm here to explain you all, and I will be helping, inshallah, all the times. Okay.
Yeah.
Okay, sir.
Yes. So I'm going to share these notes to you. Okay. So by tomorrow, inshallah, we will be practicing this, uh, the wave portion of unit 2, because we have practiced current electricity a little bit, waves, and right after this week we will be is doing past papers. Okay, we have time, so I will request you all कि अगर आप लोग please, just if you have the printed past papers with you, or if not, then you can uh, annotate on the past papers, but at least we must have the past papers. Okay. And
Okay, sir.
during that past paper discussion, we will have uh, the questions, or we will have the discussion of the papers, inshallah, discussion of the topic. Okay.
Mm-hmm.
Yes. Any question till this point?
No, sir.
Not yet, sir.
Okay. I'm gonna share the files with you, and inshallah having we will be having the worksheet. I will practice the questions with you. Don't worry. It is not that I will leave you people without practicing. I will, uh, you know, share my practicing stuff with you that we will be practicing here, inshallah. Okay. See you then.
Okay, sir.
Sure.
Allah Hafiz.
Teacher. Sure.
Hafiz. Allah Hafiz.
Allah Hafiz.